We are interested in creating swarms of autonomous aerial vehicles that are capable of navigating in cluttered 3D environments in close proximity to each other. Generally, this involves the planning of safe trajectories and the coordination between vehicles through communication and sensing to avoid collisions during flight. However, these approaches are difficult to scale to large numbers. In nature, we see several examples of swarming animals like bees, bats, and birds, which suggest a completely different approach for design and for control. As you can see here, honeybees fly in close proximity with each other in large swarms. They are remarkably robust to collisions with the environment and with each other. They are able to bounce off neighbors that get in their way. We are interested in creating robot swarms that exhibit this resilience. We explore a similar approach with small flying robots. We developed controllers that are able to recover from collisions and also a 25-gram Pico quadrotor that is capable of sustaining mid-air collisions with its environment and other robots. This allows us to use very simple motion planners that allow the robots to navigate an environment without complete knowledge of the environment. Each robot plans its own path without considering its neighbor's positions or intended motions. Instead, it relies on its ability to recover from collisions with other robots. These simulations show 100 robots flying through different obstacle fields while encountering collisions with the environment and other robots. Next, we showed that collisions of the robots with obstacles can be harnessed as a source of spatial information, which can in turn be used to construct a sparse map of the unknown environment. Next, we see that for many cases, bouncing off of the obstacle results in the robot taking less time to complete the direction reversal. Note that for the Pico quadrotor, from distances below 4.5 meters, a collision-free trajectory isn't possible, and above 9 meters, the traditional method finishes in less time. Colliding with surfaces can be used for deploying sensors like those for measuring air quality, radiation, or small payloads like magnetic LED flares as demonstrated here. Just as birds can fly through narrow gaps, our robots can swarm through small apertures without explicitly planning trajectories or coordinating with their neighbors. This experiment demonstrates the ability of a team of Pico quadrotors to fly through an obstacle-rich confined space. The robots, without any prior knowledge or map of the environment, are able to bounce off of obstacles and sustain stable flight to eventually reach the goal locations. Birds and insects are able to navigate through dense foliage while rolling and pitching and executing aggressive maneuvers. Here we show the ability of the Pico quadrotor to fly through foliage while sustaining collisions with the plant without losing stability.